What do you mean my shit isn't working? Oh. Hang on. Okay, that should be better. Continue recording. Okay, so I've gotten a lot of nervous emails about the assignment that you see in my math lab titled Final 1. That's password locked. It's not something you guys can get into, and it is not something you have to worry about. That is something that the course committee put in there so that us professors can look it over and try to come to some consensus about what the hell we're going to do for the final exam in this class. Because of course, this is usually a department final, meaning everybody takes the same final at the same time on campus. With all this COVID-19 insanity, that is not possible. So we have to try and find some solution, and that assignment is just there so that myself and the rest of the faculty can look over things. The due date is not a relevant thing. That's again, just a reminder for faculty to look at the damn thing, because so many of them wouldn't unless they were poked to. So please don't worry about the thing titled Final 1 in my math lab. That's for me, not for you. You don't need to get in there, and you cannot get in there. It is locked out for you guys. I have gone ahead and made some changes though with your homework and stuff. So all of the logarithm homeworks are now open. There is the homework 19 that was open last week, and that is going to stay open through the rest of this week, and it will close next Monday. There's also homework 20 and homework 21. Homework 20 is on properties of logarithms, and homework 21 is on solving log and exponential equations. Now, that last one, I'm definitely going to extend a little bit beyond the nominal due date there of 4/13. But the first one, homework 20, I would like for you guys to get that done by the 13th. So homeworks 19 and 20 are going to be due next Monday. Homework 21 and the associated quiz, those may be extended beyond that. It's going to depend on how quickly you guys move through the material. So I'll be keeping track of how much you guys get done. And if we have to squeeze the last little topic here, which is on systems of equations and systems of inequalities, I'm okay with squeezing that. That's not a huge topic, and it's not anywhere near as important as logarithms and exponentials are. But please make sure you're working hard on this stuff. Continue working on it now, and we'll get through everything. It's going to be okay. So today I want to talk, I want to introduce these properties of logarithms to you guys. I want to start showing you what it is logs do algebraically, and hopefully it will make sense in the context you've already seen them, where we're evaluating logs using that useful definition. And it will give you a kind of better way to look at some of the problems that maybe you haven't gotten to from homework 19, and also is, of course, necessary to approach the stuff in homework 20 and 21. So a quick word of warning or whatever. I'm recording this on my computer today, not on the cloud. And with my Calc 2 class this morning, that actually caused some trouble. For whatever reason, I guess maybe my GPU isn't capable of managing this so well. People said there was a big quality issue. So I don't know if you guys are seeing a quality issue right now. Can you make out the board okay? Can you see me okay? Does everything sound and look normal? Or are there any problems? Please let me know.
Everything looks pretty good, just the glare on like the right side like usual.
Yeah, that glare sucks, but I haven't found a way to get rid of it yet. But as long as things are legible, if you're happy, I'm happy. Okay, so logarithms continued. Last week, we worked mostly with this idea. And that's that y is equal to the base a log of x means the same thing as saying a to the y equals x. In other words, the base a logarithm of x is the power to which you need to raise that base in order to get x out. In some cases, this just gave us a new way to look at something we already knew. For example, we said that 2 is the base 3 logarithm of 9 because 3 raised to the 2 equals 9. The place I want to start going with this is to start thinking about these more in terms of algebraic properties. So once you get comfy with this idea of evaluating a logarithm, finding that number, whatever that number is, you can start thinking about these as tools for solving equations because they have this really neat property of pulling things from exponents down. So another way to define the logarithm, and the way that we're going to start thinking about these things from here, I'll call this property 1 of logs. And that is that the base A logarithm of A raised to some stuff, what should this be? This should be the number to which I need to raise A in order to get A to that stuff. Well, that's that stuff. So whatever this is, that's what this simplifies to. And the other way of thinking about this is that if you raise A to the power of the base A logarithm of some stuff, that will give you that stuff also. So logs and exponentials undo each other. And this is why they're so damn useful in equation solving. Some equations we could solve using the one-to-one property, or the mathematical term for this is by inspection. You just stare at it until you can tell. But some equations we couldn't. So we were able to solve the equation like 2 to the x equals 1 over 8 by thinking, okay, well, what power of 2 do I need to get 1/8 out? I say, okay, well, 2 to the x equals 1/8. That's the same as saying 2 to the x equals 2 to the -3. So x has to be -3. But a new way of looking at this and this new approach is what you need to solve the latter half of the problems in homework 19. That's one of the reasons I'm extending homework 19, is you start with 2 to the x equals 1/8. And you take the base 2 logarithm of both sides. Just like taking the square root of both sides, you can take the base 2 logarithm of both sides. It's an operation that you can perform on both sides of an equation. You take logs. Of both sides. It's just like square rooting both sides, or just like taking reciprocals on both sides. It's an operation you can apply to both sides of an equation and get another equivalent equation. For equations like this is the way to go, really, the top one, because it's easy, it's fast, and it doesn't involve breaking out this big-ass tool of logarithms. But you can break out this tool, and here, because the base A log of A to some stuff is just that stuff, the base 2 log of 2 to the x just simplifies to x. So this logarithm gets the x out of the exponent and brings it down. And over here, I just have whatever this number is, the base 2 log of 1/8. Now, I could, on its own, just ask you to find the base 2 logarithm of 1/8. That would be a fair question. But if we're going to approach it from this angle of, like, I'm using this to solve an equation, then we need some other way to evaluate this. So that's the first thing I want to show you today. Last week, we saw how to evaluate base 10 logs and base E, or natural logs, in the calculator. But we don't have any way to evaluate base 2 logs or base 3 logs in the calculator. So that's the first thing I'm going to show you today. It's called the change of base formula. It'll let you take that base 2 log and write it as a natural log or as a common log so that you can put it into your calculator. So one of these markers works a little better.
So, like when we take tests on these logs, will we have to show our work, or can we like just plug it in our calculator? Because I know some of these you can just plug into your calculator.
You will have to show work. So the way I'm doing tests right now in my other classes, and the way I intend to do your tests, is you will take the test online in my math lab, and you're going to need to write out all your work on a sheet of paper, like this. And then you're going to scan that sheet of paper using an app called TinyScan or CamScanner, something like that, and upload it to Canvas immediately after you finish doing the test in my math lab. The My Math Lab stuff is going to count as the multiple choice true-false first page of our test. And then the work that you upload, I will grade as the free response portion of the test. So it will be a mixture of the two, just like our regular tests. You need to show work.
So that means that we can still get, like, if we got something wrong in the problem, but we still got most of it right, we can get like
Exactly.
the points.
Yeah, precisely. This allows me to still give you partial credit if you know what you're doing, but you type something in wrong, right? There's so many reasons why I hate online tests. The biggest one is that, yeah, there's no room for partial credit. So that system will allow me to give you credit for your good work, even if the answer, the number doesn't come out right, or if you enter it wrong in the computer or something like that. Okay, but the question stands, how do I ask my calculator for the base 2 log of 1/8?
You have to go to math and then go down to the one thing where it says log base.
That is an option on some calculators. But it takes time. And not every calculator has that tool. So the real answer to this question is what's called the change of base formula. There's nothing wrong with what you said. Yeah, if your calculator has the random or the arbitrary base logarithm function, you can use that. But for other reasons, it's important that we know the change of base formula. So how do I go from one base to another base? Suppose somebody hands you the log base b of x, and you want the log base a of something, right? So right here, I have the log base 2 of 1/8. But I want to turn it into an ln, or I want to turn it into an log with the base 10. The way you do that, for any number a that you want to turn this into, this is going to be the base a log of x. So that's the base you want of the same inside divided by the base a log of the old base. So if you want to go from base b to base a, this is how you do it. For example, if I want to take my base 2 log of 1/8 and turn it into a common log or a natural log, I'm going to use a equals 10 or a equals e. So this would be the common or base 10 log of 1/8 divided by the common or base 10 log of 2, which is the same as the ln of 1/8 divided by the ln of 2. So go ahead, if you have that base b logarithm button on your calculator, go ahead and hit that. This is going to come out to -3. If I do it this way, I'll also get -3. So I'll hit ln of 1 divided by 8, close that parentheses, and then divide by ln of 2, and close that parentheses, and boom, I get -3. So this.
Yeah, I got -3.
Yeah, good. So no matter how you compute it, if you have the arbitrary base logarithm function in your calculator, you can use that. I'm okay with that. There's no harm in that. But if you don't, then the change of base formula is your buddy. He will let you turn any weird logarithm into one of these common or natural logs. Sorry, this camera's getting a little bit out of shape. There we go. Let's prop this up so it doesn't tilt. that better? That's better, right? Yeah. Oh, come on, focus. Okay. So some exponential equations like these, we can solve like using the one-to-one property like we did last week. But some of them we can't, and we need to approach this way. I think the best way to get there is to see some of these equations that we know how to solve this way, solved this way. Questions about this example? Okay. So that first property of logarithms, that's a big deal. That the base a log of a to some stuff is always just going to give you that stuff. One of the problems in your homework, I think the first problem in your homework that requires you to use this way of thinking to solve the equation looks like this. I forget what the right-hand side is. I think it's like 8. So if I want to solve e to the negative x equals 8, I need to use logarithms. There's no way for me to write this cleanly as a power of e. E is such a weird number. I'm never going to like just see it or think about it or like algebra my way there aside from using logarithms. So to do this, I take the natural log, right? The way you choose which logarithm to take is you look at the base of your exponential. The previous equation was a base 2 exponential. It had 2 to the x. This guy is a base e exponential. So I'm going to solve this equation by taking the natural log of both sides. When I do that, I get the ln of e to the negative x equals the ln of 8. According to property 1, the ln of e to the negative x is just negative x. Because remember, this is the base e logarithm of e to the negative x. So that just simplifies to negative x. And over here, I have the ln of 8. I usually write my logs with a script L. I hope that doesn't confuse you. If you don't like the script L, you can write it with a straight L. Then to finish this, I just divide both sides by -1 or multiply both sides by -1. It's the same thing. So this is what we would call the exact answer. In terms of logs. And then I can also approximate that answer as a decimal using my calculator. So I'm not going to pull up the virtual TI-83 for this. I'm just going to type negative ln of 8. Close that parentheses and hit enter. I get negative 2.07944, blah, blah, blah. So if I round that to like 3 decimal places or 4 decimal places, we'll call that 2.0794. All right, now work along with me. In your calculator, I want you to hit second and then the division symbol to type an E. So I'm going to check. I'm going to take this number and plug it in here. So I'll have E raised to the power of, that's this caret button that's right above the divide. And then I'm going to open a parentheses. I'll have negative of, and then open another parentheses, negative 2.0794. So that's going to be e raised to the positive 2.0794. The two negatives will cancel. And when I do that, I get 7.999667, blah, blah, blah. So I'm getting something very, very, very close to 8. So this is very, very, very close to the actual answer. What is the actual answer? This. And if you type this into your calculator, if you hit second and then divide to type the e, hit the caret to get up into the exponent, and then type ln of 8, it'll come out to exactly 8. So this is what logarithms do. Logarithms are powers. The ln of 8 is the power to which I need to raise e in order to get 8 out. algebraically, they let us bring things from exponents down. So the negative x was in the power of e in the original. And after I took logs on both sides, the negative x came down out of the power. Algebraically, that's the magic. And this rule can be extended a great deal. So the next thing I would like to show you is a little bit more of these properties. Questions on this example or the change of base formula? Okay. Once we're comfy with the properties, the algebra properties, I'm also going to want to look at the graphs of these log functions, right? They're interesting functions on their own. We don't just use them to solve equations, we study them as functions in their own right, especially in my field of math. They're super duper important. There's this horrible joke, what sound does a drowning analytic number theorist make? And the punchline is log, 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 log. It's bad, I know. So property one of logs. The first one is that if you take the base a log of a raised to the, I'm just going to use the symbol x now instead of the word stuff, but with the understanding that x could be anything. It doesn't have to just be the variable x. It could be a combination of variables and numbers. It could be just a number. This is x. That's because the base a log is the inverse of the base a exponential. Remember, when you compose, when you plug one function into another, if they're inverses, that should always simplify to x. The other way of saying this is that a raised to the base a log of x is x. That's the first property.
Kind of going out of focus now, like I can't even see.
Let's see.
Yes, sir.
So I'll try to stand close to the board. I think the camera tries to focus on movement. That's why I try to step out of frame. Is that better?
Yeah, that's a lot better. Thank you.
Okay, cool. Thank you for letting me know. The second big important property here is kind of an extension of this first one. What if these bases don't match? What if I take the base a log of some other exponential? Well, what happens is that this x moves down in front. This is x times the base a log of b. So I want to show you some examples with that second property. But first I'm going to list, there's a couple other big important properties here. So let's get these all in our notes in one place. You remember those rules for exponents, right? That like a to the x times a to the y is a to the x plus y. Well, the log has a backwards version of that, which says the log a of x times y is the same as log a of x plus log a of y. So the logarithm takes multiplication inside to addition outside. Just like the exponential takes addition inside to multiplication outside. It's the exact opposite because it's the inverse. Log is the inverse of the exponential. And then the last one of these important algebra properties if it takes multiplication inside to addition outside, what should it do to division inside?
Subtraction.
Yeah, and that's exactly it. So the base a log of x over y, and again, x and y could be anything. They could be numbers, functions, combinations of numbers and functions. That's the log a of x minus the log a of y. And these last two, I want to caution you can be misused. You have to remember them correctly. Addition outside is the same as multiplication inside, but there is no rule for addition inside a log. The log base A of x plus y has nothing to do with any of these. Multiplication inside is addition outside. Division inside is subtraction outside. Nothing else works. So let's use these to try and solve a slightly more complicated equation. I'll grab one from your homework. Okay. Let's start with something from homework 19, something a little later in there, something a little tough. And then we'll look at a problem or two from homework 20 as well. Let's see, I think we actually did that one last time, so let's something a little further. Yeah. So number 24 in homework 19 says that you have some population and it starts out with 150 dudes. It grows continuously by 6% per year. So remember, that's one of those situations where you use the continuously compounded interest formula. They want you to write a function that models the population and then solve an equation relating to it. What did I say, 5%? Yeah. So they tell me that a population starts with 150 dudes and it grows at the continuous rate of 5% per year. I put the little quote bunnies around continuous rate because this is one of those examples of what I would call a very contrived problem. There isn't a lot of intuitive meaning, but the use of the word continuous here tells us to use the continuously compounded interest formula. Then they first ask us to find the function that gives the population after X years. Find the function that models the population. It's a multiple choice question, but we know to use the continuously compounded interest formula. That's P e to the r. Instead of t here, I think we're using x, right? Oh no, they use t. Okay. So after t years. So this is my function. I'll call it f of t. P is always the principal or the initial value of the initial population, which here is 150. R is the continuous growth rate. E is just the constant E. So my continuous growth rate is 5%, that's 0.05, and T is my variable. So there's the function. And then in part B, they ask, what's the population after 9 years? And then in part C, they ask, how long to reach 2206 people? So what's the population? C. All right, so the solutions to parts B and C I will do on the left side. Please put these properties, these 4 properties of logarithms, somewhere safe in your notes. And then put a little sticky tab on them so you can refer back to it all the goddamn time, because you're going to need to. All right? Really understanding these 4 things and really getting comfortable using these 4 things is what all these homeworks are about. We'll work our way up to it. Yeah.
What does C say?
How long to reach a population of 2,206? So I wrote how long to reach pop 2206.
All right, thank you.
Yeah, of course. So to solve part B, after 9 years, the population will be f of 9, right? This is the population after t years. So if I want to know what's the population after 9 years, I need to plug in t equals 9. In other words, I'm looking at f of 9, which is 150 times e raised to the 0.05 times 9. So I'll need my calculator for this. I type 150 times, and then second divide to get my e, and then I hit the button right above divide to get into the power. That's that caret, the arrow that points up. And then I need to open a parentheses. If I just type 0.05 times 9, my order of operations won't work out right. That would give me e to the 0.05, and then multiply that result by 9. That's not what I want. So I type e caret open parentheses 0.05 times 9 close parentheses. When I do that, I get 235.2468 blah blah blah. Now this is a population. It's very hard to have 0.2468 people, at least if they're healthy and alive. So I would round this to the nearest whole number. I would say there's about 235 people. Part C is the one that's going to require the use of logarithms. So I want to know how long will it take, or when will the population reach 2,206? This is the population after t years. So I need to set this equal to 2,206 and try to solve for t. So that's the equation I need to solve. And this could not be done without logarithms. We could approximate it in our calculator like we did with those half-life problems last week. But now we can get an exact solution. First, I have to get the exponential piece by itself. Only then can I take logs. So first you got to get rid of this 150. You got to have e to some shit, and then you can take logs. So I divide both sides by 150 first. Now I need to get my variable down out of that exponent. And the way to do that is to take logarithms. It's not going to come down on its own, though. So we're going to need property 2, the second property that we talked about with those logarithms. I take the ln of both sides. That looks like this. And now my right-hand side is going to stay the same. My left-hand side is going to simplify to 0.05 t times the natural log of e. So I'm going to move back over to the other side of the board here, so I can do this really carefully. That second property of logs says that if you take the log of a power, the power comes down. So this is 0.05 t times the natural log of e. And then the right-hand side is still what it was. It's the ln of 2206 over 150. The natural log of e, check it in your calculator. This is 1. It's the power to which I must raise e in order to get e. Well, e to the 1 is e. So in other words, my left-hand side is now just 0.05 t. Because it's being multiplied by 1. And then finally, to solve for t, I divide by this 0.05. And that's your exact answer in terms of logarithms. And most of us, myself included, don't have a damn clue how big this number is looking at it in this form. So I would like to approximate it with the calculator to get a better feel for it. So I want to do one of these on the virtual TI-83 so you guys can follow the calculator work. On how to put b in the calculator. So if you want to enter a different base logarithm, the easiest way is to use the change of base formula that I showed at the beginning of class. Another option, depending on the calculator you have, is to hit the button that says math, and then just search around until you find the arbitrary logarithm function. I think it's under, where is it? It should be under math somewhere, near the nth root button. I haven't fiddled with it. I don't even know if the one I'm using has it. But the change of base formula is the good answer to that. And yeah, we can take a look at it at the end. Before we do that, let me first show you how to enter this guy in. So I'm going to share the VTI-83. I want to take this number, the ln of 2206 divided by 150, all divided by 0.05, and put that in the calculator. So I come down here to ln, and it'll open up parentheses for me, so I don't need to open one. 2206 divided by 150. And then I close that paren, because the only thing I want inside the logarithm is that ratio. And now I divide that whole thing by 0.05. And that's 53.766, so about 54 years. So there was a question, how do you change the base in a logarithm? How do you put a different base log in the calculator? Before I return to that, questions on solving this equation. This is a big deal. So everything from here down over to the other side of the board. This is what the majority of your new homeworks are going to look like. They're going to be solving exponential equations by taking logs. What looks weird? What feels funny? What are we wondering? Things feel mostly okay? All right, so I'll return to the change of base thing for a minute, and then we're going to look at a couple other problems. If I wanted to enter like log 5 of 12 in the calculator, use change of base. That formula says that the base b logarithm of x is the same as the base a logarithm of x divided by the base a logarithm of b. So if you want to go from some stupid base like 5 to a base like 10 or e, you take the base you want of the inside divided by the base you want of the old base. So for example, to enter the base 5 logarithm of 12, I would treat that as I would use a equals 10 here maybe, and enter it as the common log of 12 divided by the common log of 5. Or I could use the natural log. I could enter it as the ln of 12 over the ln of 5, right? Because you do have an log button and you do have an ln button. You could also write this as like the base pi log of 12 over the base pi log of 5, but why on earth would you? So the change of base formula is this. We can use it to take a weird base into a normal base, like the base 10 or base e. Or you could take a weird base into another weird base if you want to, but there's no reason to ever do that. For the sake of calculation, for the sake of using your calculator, these are the two that you're going to use most of the time. I want to return to one of the motivating questions that we looked at when we were first starting to talk about logs. And that was the equation 2 to the x equals 3. Okay, from looking at the graph of 2 to the x and the graph of 3, like y equals 3, that line, we're able to say that, yeah, for sure, this has a solution. And then in terms of logarithms, we're able to write down that solution. If I take base 2 logs on both sides, that equation becomes this. And then the base 2 log of 2 to the x, that's just x. Or you can think of the x as coming down, right? This guy moves down here as a constant multiple, or as a multiple. And the base 2 log of 2, just like the ln of e, is 1. So this is just the same as saying x equals the base 2 log of 3. And last time we weren't able to get an approximation for this because we didn't have the ability to put that in our calculator. But now we do. So the base 2 log of 3, I could enter that as the ln of 3 divided by the ln of 2. Go ahead and do that with me. On my calculator here, I'll type ln 3, close parentheses, divide by ln 2, close parentheses. And I get 1.549, blah, blah, blah. $1.58496, let's say. Now again, along with me in your calculator, take 2, hit that button above divide to get into the power, so raise 2 to the power of, open parentheses, 1.58496. I get 2.999999948. Very, very, very close to 3. So this is what logs do. Logs bring things down out of powers. So I hope that helps you a little more comfy with the change of base stuff. I want to return to some some more of those tricky homework problems. I think we have time for one more. So I'm going to grab something from the very end of homework 19. All right. So problem 26 gives us this function t of x equals 20 plus 80 times e to the negative x. And I will jump to the hard part, which says, how long does it take for this thing to get to 50? So in other words, I want to solve equals 20 plus 80 times e to the negative x. The trick with all these equations that involve exponential functions, equations where your variable is in the power, first you need to isolate this term, isolate the exponential term, and then you're going to take logs. So if I isolate the exponential here, that means I subtract 20 from both sides to start. Then divide both sides by 80. 30 divided by 80 is 3 over 8. And then I take natural logs on both sides. When I take the natural log of e to the negative x, I just get negative x. And now I multiply both sides by -1 or divide both sides by -1 to find x equals negative ln of 3 over 8. I want to show you something cool. The second property of logarithms that I showed you is that a multiple out front is the same as a power inside. So check this with your calculators. This is the same as the ln of 3/8 to the -1, which is 8/3. Okay, so type in your calculator negative ln 3 over 8. I get 0.9808 blah, blah, blah. And now, separate from that, type ln 8 over 3. I get 0.9808 blah, blah, blah. Same thing. So here I'm using that rule that says a power inside can come out front as a multiple, but I'm using it backwards. I'm using it to bring this multiple of -1 inside as a power. And getting comfy with those properties is going to be the big trick as you finish up homework 19 and get into homework 20. All right? On Wednesday, we're going to just solve a bunch of problems from homework 20. You've got the tools now. It's just going to be a matter of practice. And then on Friday, we'll talk a little bit about the graphs, and we'll move a little bit more towards studying these things as functions in their own right, try to get you ready for that last bit of logarithm homework. Don't panic about due dates right now. All right, the current homework, homeworks 19, 20, and 21 are going to stay open for a little bit. Homework 19, I think, will probably close next Monday as the normal schedule. But homeworks 20, 21, and the associated quiz will probably stay open for at least 1 week after that. The semester is going to end. We are going to run out of time here. And so we will need to get through that last bit of material, which is on systems of equations and systems of inequalities. But that material is very easy compared to this material. So we want to take our time here. We really want to take our time and work hard on this stuff. If you get stuck on anything, don't be shy about sending me a Canvas message. I have an office hour tomorrow from 9 to 11. It's that same link that's up in Canvas. Feel free to bring problems to our class on Wednesday or to come by the office hour with any questions you may have, okay? All right, is there anything you guys would like to ask about or talk about in this last minute or so before we have to go? Okay, then that's where we're gonna leave this. I am recording this on my local machine rather than on Zoom's cloud, so it might take a little bit longer for things to show up, for me to update that announcement with the link to the video, but when I do that, the video should work because I'm just going to upload it to YouTube. We're not going to fuck with Zoom anymore. Zoom's been shitty about this. So be a little bit patient waiting for the recording to come up, but when it comes up, it should work. No bullshit. All right? Okay, come by my office hour, send me a Canvas message if you have any questions. I will see you guys on Wednesday.